So with this model, right, now let's try to analyze the cost of certain collectives. So let's start with the simplest collective. We'll start with broadcast. How costly is broadcast? So what is the algorithm, right? You're given a complete leak, all the nodes are connected to each other, right? So you have 1 to p nodes and every node is connected to each other by a link, right? You can assume that. So what kind of an algorithm can you use? We'll use the numbering 0 to p minus 1, okay? So let's say node 0 has data, right, and it wants to send to all the other nodes. So one trivial algorithm is that 0 sends out the data to all the other nodes, right, one by one. That is clearly not great, right? What is the problem with that? What is the cost of that? It will have to send p minus 1 times, right? And what is the cost of each communication? Ts plus mtw, right? Can you do better? So we discussed this already, if you remember.
0 sends to 1, then 0 and 1 sends to...
Yeah. So that's called recursive doubling or recursive halving, depending on what communication you're performing, right? But how does this work? So 0 will first send to p by 2 minus 1, right? So this will be one communication, right? So this will take time Ts plus mtw. Now in the next iteration, 0 will send to p by 4 minus 1 and p by 2 minus 1 will send to 3 p by 4 minus 1, right, and so on. Yeah. There are various ways of thinking about it, and one simple way is that think of this as log p bits, right? So there are p nodes, so it can be represented using log p bits, right? So a node is going to look something like this. Let's say its ID looks like this, right? y1, y2, y3, y log p. These are the bits, right? So in the first iteration, the data is with node 0, right? So node 0 is going to send to the node which has ID, the first bit flipped, right? So 0 looks like this. Let's say that there are 16 nodes, right? So 0 will send to, it will just flip the first bit. So it will send to 1000. Okay, slight correction over here. So in the first iteration, 0 will send to p by 2, right? Not p by 2 minus 1. And in the next iteration, so these should all be, yeah, let's check that. So in the first iteration, basically you just flip the first bit, right? So this is 0, this is p by 2, right? In the next iteration, both of them will flip their second bit, right? Second from the left, right? So this will send to 0100, right, which is p by 4, yeah, and p by 2 will send to 1100, right? It will just flip its second bit. Yeah, so it's quite simple. So if you look at 8 nodes, right, what's happening in the first iteration? It's sending it over here, right? After this, node 0 will be responsible for, in the first iteration, node 0 was responsible for sending to everybody, right? After it has sent the data to this node p by 2, it will take care of the first half and this node will take care of the second half. How do they take care of it? So in the second iteration, it will send it to this node and this will send it to this node, right? And now you can divide it into 4 parts, right? So this node will be responsible for this region, this node has data, it will be responsible for this region, this node has data, it will be responsible for this region and this for this. Yeah. And finally in the last round, this will send here, this will send here, this will send here, this will send here, right? So how many rounds does it take? So what is the cost? Let's analyze the cost now. How many rounds are there? In case of p nodes, what is the total number of rounds that you will have? In the first round, 1 node is sending the data. In the second round, 2 nodes are sending the data. In the third round, 4 nodes will send the data. So when will you cover all the nodes? How many rounds? Log p, right? So the cost will be, there will be log p rounds, and in each round, what is the cost? The cost is Ts plus mtw, right? because again we are assuming a clique, right? So any two nodes communicating, as long as the same node is not sending twice or receiving twice, right, the cost will be TS plus MTW. Okay. So that's the cost of doing a broadcast using recursive doubling, right? So it's clearly better than this cost, P minus 1 times TS plus MTW, right? And it makes perfect sense. So it's the obvious way to do it. What's good about it is that on most architectures, it works quite well. Okay, so let's examine the architectures. So on a clique, it's going to do well, right? Although the Hockney model is designed ignoring the underlying topology, but let's see how it actually does when you're given the topology. So in a clique, anyways, Hockney model is designed for the clique, right? So it will take the same cost on a clique. Now, what would happen if you have a linear array? Yeah. So in the first round, what is the communication happening? This is the communication happening in the first round. In the second round, what is the communication happening? This and this. These are both on disjoint set of links. Yeah, there's no overlap of the links that they're communicating on. In the third round, what is the communication that's going to happen? Well, this will send here, this will send here, this will send here, this will send here, right? So again, disjoint, right? Okay. Now let's go beyond a linear array. So linear array also, it will be the same cost, right? Okay. What about mesh? Let's take a 2D mesh of size root p cross root p. So let's just take 4 by 4 for illustration purposes. So let me number these nodes, right? So I'm going to number them like this. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. Okay. Now let's see what happens in the first iteration. 0 sends to 8, right? So it's going to send over here. What happens in the second iteration? So in the second iteration, 0 is going to send to 4 and 8 is going to send to 12, right? And then in the third iteration, 0 would send to 2, 4 would send to 6, 8 would send to 16 and 12 would send to 14. And in the last iteration, again this, right? So is it clear? So again, as you see, right, all the communication links in any given iteration are independent, right? So even on a mesh, right, the recursive doubling or recursive halving gives you the same cost. As a matter of fact, if you look at it carefully, what is actually happening is that first the broadcast happening on the column, on the first column, right, using the same algorithm, right, because 0 sent to 8 and then in the second iteration 0 sent to 4 and 8 sent to 12, right. If you just look at the first column alone, it's nothing but the same algorithm being run on the first column. And if you look at the third and fourth iterations, you'll see that it's nothing but each of the rows independently executing the same algorithm, right. Okay, crux is the cost is the same. All right, and let's go to hypercube. Yeah.
It was to be log p by 2 square.
Sorry?
Square of log p by 2.
Square of log p by 2. It's root p.
Yeah. Root p means log p by 2.
Not square, right? 2 times?
No, square.
Why square? 2 times,
2 times.
right? So p by 2 and 2 will cancel out. So you'll get back log p. All right, so this is your hypercube. And as we discussed, right, if you remember, I'm going to number them like this: 0, 1, 2, 3, 4, 5, 6, 7, right? You remember the numbering for hypercube? If you look at the nodes adjacent to every node, they differ in exactly 1 bit, right? If you look at 0, its neighbors are 1, 2 and 4, They differ in exactly 1 bit, right? So last time we covered the construction for hypercube, how you construct a hypercube, and this follows from that, right? So again, if you execute this algorithm, the recursive doubling, you'll see that in the first iteration what happens, 0 sends to 4, right? That's along one of the 3 dimensions. So there are 3 dimensions over here, right, in this hypercube. I mean, you can generalize this to log p dimensions, but essentially in the first iteration you're communicating along the first dimension. In the second iteration, 0 would send to 2, 4 would send to 6, right? That's communication happening in the second dimension. And finally, in the third iteration, 0 will send to 1, 2 will send to 3, 6 will send to 7, and 0 will send to 5, right? And you can see it's communication happening along the third dimension, right? Or even if you look at it in terms of bits, right, that's easier. Again, the whole point is that if you look at nodes along a certain dimension, they differ in exactly the same bit, right? That's the property of the hypercube. So if you look at 0, 0, 1, 2, 3, right? If you look at that plane on the further end, 0, 1, 2, 3, every node on this side differs exactly in the first bit out of the 3 bits, right? The leftmost bit. If you look at the top plane, 0, 1, 4, 5, what is the difference if you go down? It's exactly in the second bit for all 4 of them, right? And if you look at the plane going from left to right, yeah, if you look at 0, 2, 4, 6, when you go to the right, it's all differing in exactly the last bit, okay? So that's the useful property of the hypercube, which you can use in lots of algorithms, right? The crux is that cost again turns out to be the same, right, even in the hypercube. So whatever architecture you have, the recursive doubling turns out to be quite good for broadcast, right? It maps quite well. Of course, if instead of root p by root p, if you have something else, right, m by n, then it may not work as efficiently, right? But the point is that in practice it does well on most architectures for lots of collectives. So there are implementations based on recursive doubling. All right, let's look at one more architecture. This is the balanced tree, right? So in the balanced tree, the nodes are all at the bottom, right? And in between you have switches. So again, how would recursive doubling work over here? Well, 0 would send to 4, right? That would traverse this path. In the second iteration, what would happen? 0 would send to 2 and 4 would send to 6. And what would happen in the third iteration? 0 would send to 1, 2 to 3, 4 to 5, and 6 to 7. Again, in any particular iteration, the links are disjoint, right, over which communication is taking place. So again, the cost is the same. So that's basically broadcast, how you do a broadcast, right? And the cost turns out to be log p times ts plus mtw, right? That's typically the cost. Okay. Actually, the cost for broadcast and reduce is the same. Reduce is just broadcast done in reverse, right? You can see that, right? Let's look at one of these. The remaining will be obvious, right? Let's look at linear array. So how would it work in case of reduce? So you remember the reduce operation, right? You have an array of size m on all the nodes and you're supposed to do element wise some operation, let's say addition, right, across all the nodes. So in the first iteration, what will happen? Just follow the algorithm in the reverse direction, right? So node 7 will pass to node 6 all its data, right? Node 5 will pass to 4, 3 to 2, and 1 to 0. Yeah? So now what will this node do? It will simply add up the data, right? Whatever addition it has to perform. It has 2 arrays of size m, it will do element wise addition, right? Similarly, this node will do the same, this node will do the same, this node will do the same. Now what will happen in the next iteration? In the next iteration, this node will pass all the data over here and this node will pass all the data over here. It's exactly the reverse of what happened in the second iteration of the broadcast, right? You can see that. So again, it will add up the data that's coming from both ends and send the data to this one in the third iteration. That's it, right? So the implementation for reduce is nothing but just the reverse of the implementation of broadcast, right? So it's called a dual of broadcast. Okay.